Let's see how we can use this important theorem. We'll revisit the question of when a linear function is invertible. We'll prove the following theorem. Let f be a linear function from big V to big W. Then f is invertible if and only if its kernel is equal to 0 and the dimension of the domain equals the dimension of the codomain. I like to interpret that condition as saying the domain and the codomain are basically of the same size so that they can be matched up. Here's the proof. Well, we saw before that a linear function f is one-to-one if the dimension of its kernel is 0 and is onto if the dimension of its image equals the dimension of its codomain. So a function f is invertible if both conditions hold. That is, if the dimension of the kernel is 0 and the dimension of the image equals the dimension of the codomain. But now we have an additional tool, the kernel image theorem, which tells us that the dimension of the kernel of f plus the dimension of the image of f equals the dimension of the domain. So using that, the dimension of the kernel equals 0 and the dimension of the image equals the dimension of the codomain, if and only if the dimension of the kernel equals 0 and the dimension of the domain equals the dimension of the codomain. And that completes the proof of the linear function invertibility theorem. Now we'll prove an analog of the kernel image theorem specifically for matrices. Apply the kernel image theorem to the function f of x equals a times x. Then the kernel of f is just the null space of the matrix A, and the dimension of the image of f is the dimension of the column space of A, which is just the rank of A. Now we define the nullity of a matrix to be the dimension of the null space of A. Then the rank nullity theorem states that for any n column matrix A, the nullity of A plus the rank of A equals n. This is a direct translation of the kernel image theorem into the terminology of matrices. With what we now know, let's return to the checksum problem. Recall we defined a checksum function that takes n vectors over GF2 and maps them to 64 vectors over GF2. The function is defined in this way using dot products with 64 vectors, A1 through A64. We had an original file we represented by an n vector p, and the transmission error represented by a vector e. So the corrupted file is p plus e. And we were interested in finding out the probability that the corrupted file had the same checksum as the original file. We saw that if the error was chosen according to the uniform distribution, the probability that the corrupted file has the same checksum as the original file was 2 to the dimension of v over 2 to the n, where v is the null space of the matrix whose rows are these vectors a1 through a64. Well, it's easy to choose a1 through a64 so that the rank of this matrix A is 64. In fact, just choosing random vectors will probably work. Now, the rank nullity theorem tells us the rank of A plus the nullity of A equals n. Now, the rank of A, we said, was 64. The nullity of A is the dimension of this vector space V, the null space of the matrix. So that's equal to n. And that shows that the dimension of V is n minus 64. Plugging that into our formula, we get that the probability that the corrupted file has the same checksum as the original file is 2 to the n minus 64 divided by 2 to the n, which is 1 over 2 to the 64, a tiny, tiny number. So there's a very tiny chance that a random change will go undetected by the checksum function. Now let's use the rank nullity theorem to help understand when a matrix is invertible. Let A be an R by C matrix. Then A is invertible if and only if the cardinality of R equals the cardinality of C and the columns of A are linearly independent. That is, A has to be a square matrix. Here's the proof. Define the function f by f of x equals a times x. Then A is an invertible matrix if and only if f is an invertible function. And the function f is invertible, we know, if the dimension of its kernel is 0 and the dimension of its domain equals the dimension of its codomain. That is, if the nullity of the matrix A is 0 and the number of columns equals the number of rows. Well, the nullity of a matrix A is 0 if and only if the dimension of the null space of A equals 0, which is true if and only if the null space of A consists just of the 0 vector. That is, if the only vector x, such that AX is the 0 vector, is the 0 vector itself. And that's true if and only if the columns of A are linearly independent, by the linear combination's definition of matrix vector multiplication. And that completes the proof. So, for example, this matrix cannot be invertible because it's not even square. This matrix is square, and its columns are linearly independent, so it is an invertible matrix. And here's a matrix that is square, but its columns are not linearly independent. You can get the third column by adding the first two, so it's not invertible. Now we can show that the transpose of an invertible matrix is itself an invertible matrix. Here's the proof. Suppose A is an invertible matrix. We've written it in terms of its columns. The matrix is square, and the columns are linearly independent. Let n be the number of columns. Then the rank of A equals n. And because A is square, it also has n rows. Here they are. And by the rank theorem, its rows are also linearly independent. Now, the columns of the transpose of A are the rows of A. So they're linearly independent as well. And of course, the matrix is square. Its columns are linearly independent. So we can conclude that it's invertible. Let's see what else we can learn about matrix invertibility. Earlier, we proved that if A has an inverse, then the product of A with its inverse is an identity matrix. And we might be tempted to conjecture the converse. That is, if B times A is an identity matrix, then A and B must be inverses. Well, that doesn't turn out to be true. But if we add an additional condition, it is true. And that condition is that the matrices have to be square. So suppose A and B are square matrices such that B times A is an identity matrix. Then A and B are inverses of each other. To show that A is invertible, since we already know it's square, all we have to do is show that its columns are linearly independent. Well, to show that the columns of A are linearly independent, let U be any vector such that A times U equals 0. That is, A times U is a linear combination of the columns of A. And we need to show that the coefficients, the entries of U, have to therefore all be 0. We're using this equation. Multiplying this equation by B on both sides gives us B times A times U equals B times the 0 vector, which of course is the 0 vector. On the other hand, this quantity is equal by associativity to this quantity. Now B times A is the identity matrix. So B times A times the vector U is the identity matrix times U, which is U itself. Well, that shows that U must be equal to the 0 vector. That shows that for any linear combination of the columns of A that equals 0, the coefficients of that linear combination must be 0. And that shows that the columns of A are linearly independent. So we've been able to show then that A has some inverse. It's written A to the power of minus 1. Now we have to show that B is that inverse. Well, we know A times A inverse is an identity matrix. We know that B times A is the identity matrix. Well, let's multiply that on the right by A inverse. We get B times A inverse equals the identity matrix times A inverse. We can simplify the quantity on the right. The identity matrix times A inverse is just A inverse. We can use associativity on the left. And now we have A times A inverse, which we know is the identity matrix. And B times the identity matrix is B. So we've shown that B is equal to A inverse. And that completes the proof.